Hey there. So, when you pull out your phone to find the nearest coffee shop? You're using this incredible global system, right? But what you're using is it's just the tip of the iceberg. Today, we're going to dive into the other kind of GPS, the kind with a precision so insane, it's literally what our modern world is built on. So, let's figure out how they do it. Okay, so think about it like this. On one side, you've got your phone. It gets you within what? 10, maybe 20 meters of where you're going, which is awesome for not getting lost, for sure. But then on the other side, you've got the professional stuff, what they call GNS. And here we are talking about accuracy down to the millimeter. This isn't about finding a pizza place. This is about making sure a bridge actually meets in the middle or that a skyscraper is perfectly vertical. So how in the world do they do that, right? What's the secret sauce that takes a good enough signal and makes it surgically precise? It's not just about having a fancier antenna or a more expensive receiver. Nope. The real secret is something way more fundamental, and honestly, it's something totally invisible to most of us. And that brings us to the core idea here, the geometry of accuracy. It's easy to think that more satellites equals a better, stronger signal. But the pros? They know it's not nearly that simple. The single most important thing isn't how many satellites you can see, it's where they are in the sky. Yeah, you heard that right. The biggest thing that can mess up a super precise measurement isn't some glitch in the satellite's atomic clock or a cheap piece of gear on the ground. It's simply the geometric layout, the shape that you and the satellites make together. So the obvious question is, how do you even measure something like that? Well, they have a name for it. It's called dilution of precision, or just DOP for short. The easiest way to think about it is like a grade or a score for the satellite layout at any given moment. A low DOP score? That's an A+. It means the satellites are in a perfect formation. A high DOP score? That's a failing grade, and it means any tiny error is about to get magnified a lot. So what does that good geometry actually look like? Well, the analogy they use is perfect. Imagine you're trying to pinpoint a sound. It's way easier if you have friends listening from all around you, right? Not if they're all bunched up in one corner. It's the exact same thing with satellites. The perfect setup is having them spread out wide across the sky, one ideally right overhead, and the others spaced out in every direction. Together, they create this big, strong pyramid shape with your receiver at the bottom point. And that strong shape is what squashes down any potential errors. And on the flip side, this is bad geometry. See how the satellites are all huddled together in one little part of the sky? The shape they make with the receiver is, it's kind of flat and weak. The angles are tiny. And what that means is that any little hiccup, a tiny error in timing, gets blown up, sometimes massively. Your accuracy just goes out the window. And that is why just having a signal is nowhere near enough. It's the quality of the geometry, that's the whole ballgame. And the pros, they have a non-negotiable rule for this. For any serious survey work, that GDOP score has to be under 6. That's the magic number. If it's anything higher than 6, the data is considered unreliable. They won't even start. Seriously, they'll just pack up their gear and wait, sometimes for hours, for the satellites to move into a better formation. So you might be thinking, how do they make sure they don't waste a day just waiting around? Well, this incredible precision is absolutely not an accident. It's the result of some serious, meticulous planning that starts way before anyone even thinks about stepping outside. It all kicks off with what they call a pre-survey playbook, and it's all done from the comfort of the office. There are 3 big steps. First, they pick out potential locations right on a map. Second, they figure out the absolute perfect time to go out and measure. And third, they calculate exactly how long they need to stay at each spot to get the accuracy they need. And picking a point isn't as simple as just dropping a pin on a map. A surveyor is looking for a whole checklist of things. They need a crystal clear view of the sky with nothing blocking it from about 15 degrees off the horizon all the way up. They have to stay away from anything reflective, like big glass buildings or even a lake, because that can make the signal bounce all over the place. They call that multipath. And yeah, on top of all that, they gotta avoid electrical interference and, actually be able to get their truck there. So how do they find that perfect time slot? They use special software that creates something called a sky plot. Think of it like a crystal ball for satellites. It shows them exactly where every single satellite will be at any time of day, yesterday, today, or a week from now. This lets them literally look into the future and find those perfect little windows, maybe just an hour or 2 long, when the satellite geometry is going to be absolutely perfect, with the lowest possible dope. And this is where all that homework really pays off. It's a simple formula. Better geometry means less time on site. The better the plan, the less time a surveyor has to sit at each point collecting data. So this isn't just about being accurate, it's about being efficient. It saves a ton of time and money. This table gives you a really clear picture of what we're talking about. Look at this. To get a precise measurement between 2 points just 1 kilometer apart, they call that a baseline. You might need to record data for 20 to 35 minutes. But stretch that out to a 20-kilometer baseline, and suddenly you're looking at up to 90 minutes. The farther apart the points are, the longer you have to listen to the satellites to weed out all the errors and lock in that millimeter-perfect position. But of course, there's a classic saying, a map is not the territory. What looks perfect on a computer screen can be a total mess in real life. And that brings us to the next absolutely critical step, getting out there and scouting. It's officially called field reconnaissance, but everyone in the business just calls it a recce. And it is an absolutely mandatory site visit. It's where a surveyor physically goes out to see if the spots they picked on the map will actually work. Because that empty field on last year's satellite photo might have a brand new cell tower or a bunch of overgrown trees in it today. When they're out on a recce, surveyors are basically detectives. They're hunting for anything that could sabotage the plan. Is there new construction that's blocking the view of the sky? Is there a new high-voltage power line nearby that could cause interference? Or is there something as simple as a new fence with a locked gate that means you can't even get to the point? This is where the beautifully crafted plan smacks right into reality. So once a spot has passed this real-world inspection, it gets monumented. And that's exactly what it sounds like. They put in a permanent physical marker. We're talking a steel rod driven into the ground and set in concrete, often with a brass cap on top. It's like putting a permanent stake in the ground so that this perfectly planned, perfectly vetted spot can be found and used again for years to come. Okay, so now we have our points. They've been selected in the office, they've been scouted in the field, and they've been physically marked. Now it's finally time to pull all those threads together into the master plan for the actual survey. This master plan has a name, the observation scheme, and it's so much more than just a to-do list of places to visit. Think of it more like a complex choreography. It's a detailed schedule that lays out exactly which points get measured, at what time, for how long, and in what specific order. The whole point is to build this powerful, interconnected network where every single measurement helps to double-check all the others. A really strong scheme is all about having built-in checks and balances. You always connect every news station to at least one other one, creating redundancy. Basically, you're measuring more than you technically have to, just so you can cross-check everything for errors. For the most important jobs, they create closed loops, measuring from point A to B to C and then all the way back to A. When you get back to the start, everything has to line up perfectly. And the final, crucial step is tying this whole local web of points into the national grid, which gives it absolute, rock-solid accuracy. So really, the next time you're driving over a huge bridge or looking up at a skyscraper, or even just walking down a perfectly straight road, just take a second to remember this. All of it, every single piece of it, is standing on top of this invisible foundation, a hidden network of points that was planned with pure geometry, double-checked in the real world, and measured with a precision that is just staggering. It's kind of a powerful thought, isn't it? That our whole world is put together with this level of meticulous care that we just never see. It really makes you wonder, what other incredible, invisible systems are out there, quietly holding everything together for us, every single day?